Okay, so with respect to the details of the presentation, I'll go through a little bit of a background of seismic and seismic hazard in Australia, so what we know about it to date. And then I'll talk about some of the activities that we're doing at GA to try and better understand our knowledge of seismicity and seismic hazard within the country. So specifically looking at the earthquake geology, some of the work we're doing to remediate the earthquake catalogue, some of the ground motion research, and then go into the hazard modelling itself. Then I'll focus specifically on the latest update we did to the National Seismic Hazard Model, which was the NSHA 23. And then talk about some of the ongoing challenges that we do have in Australia. Then I'll talk a little bit about a cautionary tale about how we're going through the process at the moment to integrate modern day seismic hazard information into the building code. And then finally, talk a little bit about the National Seismic Hazard Model guidelines that a group of us will be talking about this afternoon. So there's a dedicated session to that at 5 o'clock tonight, well, this afternoon. Okay, so most people think about Australia as being seismically quiet, but yes, we do have earthquakes. And so I'll just get my pointer up so people can actually see. These up or not? Okay, so hopefully people can see that. Yes. So whilst Australia is considered to be a relatively low seismicity area, we do have high concentrations of earthquakes in certain areas. So specifically in the Eastern Highlands here, which is that was the most significant earthquake was the 1989 Newcastle earthquake. Again, relatively moderate magnitude, 5.4, but it occurred directly beneath the town centre of the city, well, the city of Newcastle. And it still ranks as one of Australia's most costly natural disasters. Oh, sorry, I'm getting an Adobe. Okay, all right. And I'll focus a little bit more about this earthquake and its relation to the earthquake loading standards, the AS 1170.4, later in the presentation. 2010, there was the Kalgoorlie earthquake. Again, relatively small magnitude, but did quite a lot of damage to unreinforced masonry buildings in the town of Kalgoorlie. In Central Australia, there was, in 2016, magnitude 6.1 Petermann Ranges earthquake. Again, that earthquake left a surface rupture length of around about 20 kilometres, vertical displacements up to 1 metre. Fortunately, it was in a pretty remote area, so no damage resulting from that event. Interestingly, just a couple of weeks ago, there was another magnitude 5.4 here with a surface rupture length of around about 8 kilometres. So it is an area of relatively high seismicity. A 6.6 off the coast of Broome, off northwestern Australia. So that earthquake was felt from Darwin in northern Australia down to Esperance in southern Australia. So Again, gives us a bit of a picture of the attenuation of ground motions throughout the Australian continent, and how efficient the seismic wave path is through the continent. And then finally, in 2021, we had the Woods Point earthquake, which occurred in the Victorian Highlands. But that actually did quite a lot of damage to unreinforced masonry buildings in the city of Melbourne, around about 130 kilometres away. So we were fortunate at the time; everyone was under COVID lockdown, so there wasn't actually anyone wandering the streets at the time. So fortunately, there weren't any casualties associated with this one. Okay. So now just a little bit of information about Geoscience Australia. I sit within the community safety branch, and there are several sections within that. So there's the observations, operations and data. So this is the group that runs the seismic networks. We have our earthquake and tsunami warning section, which is a 24/7 system that does all of the earthquake alerting. The natural hazard section, which is the area that I sit in, which is responsible in particular for the development of the national seismic hazard assessments. And then we have our vulnerability and risk section. So you can see the transition of I guess, the seismic value chain as we go from the seismic networks through to the vulnerability and risk. But also in our section, because we are really the scientists of the branch, we also provide advice and information to our observatory, and work directly with our networks folks. So when we see issues with calibration of seismic sensors and so on, we work quite closely with them, but also working to install aftershock monitoring networks and so forth. Okay, so I guess in terms of some of the specific activities that we do within our team, so we have a relatively large team looking at paleoseismology and neotectonics, which might seem a little strange for a low seismicity area. But I guess in Australia, it's a fairly arid continent. There's not a lot of vegetation, not a lot of erosion. So a lot of prehistoric earthquakes are preserved quite well in the landscape. And so we have around about 400 earthquakes that we suspect to be active features that have been mapped. Not all of them have been investigated in detail. But these are important to assess the hazard for, say, critical assets and major population centres. So I guess what we do is we lead the investigations on some of these activities, and also develop the Neotectonic Features database, which is there's a link there for those people quick enough to look at it. But yeah, just some of the activities that we've done recently. The top image of my colleague James, I'm just pointing to an excavation or trenching that we did in March, just a couple of months ago. And saw this, beautiful displacement of an organic paleosol, probably less than 5,000 years old, so a relatively recent surface rupture in Australia's history. Not so sexy, but probably more important for seismic hazard estimation is the work that we're doing to remediate the catalogue. So I think, as Kirsty mentioned in her presentation, most of GA's catalogue is still fundamentally based on local magnitudes, but unfortunately there were differences in how those local magnitudes have been calculated over time. Particularly the use of, say, Californian-based attenuation models versus Australian-based attenuation models. Differences in Wood-Anderson calibrations and so on. So what gain factors are used for the Wood-Anderson instruments in calibrating your local magnitudes. So the first step we do before we can even get to a homogenised moment magnitude catalogue is we need to homogenise our local magnitudes. So that's the plot that you see up in the top, just looking at the cumulative number of both magnitude 4.5 and magnitude 5 earthquakes. So the orange line is before, the blue line is after. So you can see that a lot of the work we've done is actually reduced the local magnitudes of these earthquakes. Then we need to convert those to moment magnitudes, and we use our conversion equations, which are based on locally derived data. Because these are non-linear relationships, so you can see that through here, they actually lead to relatively high B values. And of course, that led to a lot of consternation amongst the seismological community, because everyone told me, well, B value in Australia is between 0.8 and 0.9. You're getting values of 1.2, which is not characteristic for historical hazard assessments in the country. So I did this sanity check in terms of what do these B values that we're getting out at the moment make sense? So what I did is I simulated an earthquake catalogue, assuming a B value of 1.2. I get out a B value of 1.24. So good, fair enough. With each of those earthquakes within that catalogue, I randomised the number of stations that would have recorded it, and then randomised the distances at which those stations would have recorded that. Then simulated the ground motions and calculated Wood-Anderson magnitudes for each of those recordings. Then I applied two different local magnitude equations, one developed for Australian earthquakes, the Michael-Lieber and Maliphant relationship, 1992, and the Bakken-Joyner relationship, which is a Californian relationship. And you can see quite clearly that those B values lie within that predetermined or preconceived notions of what those B values should be in a place like Australia. So that was a good check and also useful information to provide back to the local community. But this work is certainly not finished and it's ongoing. We're also doing quite a lot of work at the moment to uplift our ground motion database. So we've been fortunate, unfortunate in some ways, that our permanent monitoring is still pretty sparse by global standards. We're a big continent, it's difficult to get places. But we are fortunate that there has been some temporary networks that have recorded in really high detail some moderate to large earthquakes. And I just point out a news clipping here from a magnitude 4.7, which was right in the middle of one of these temporary deployments. Fortunately, the RAM was okay. But what we've been doing, I guess these temporary deployments also bring additional challenges in terms of characterising the site conditions for these sites. So what we're doing is we're going back and revisiting some of these temporary deployments and doing passive array work to try and better characterise the VS30s and other site conditions for these temporary deployments. So in doing that, we're bringing all that together and have just published the Australian Ground Motion Database, which is now online. I'll show that in the next slide. And extensively reviewed a lot of the station metadata so that we can bring in a lot of the older legacy data as well. So I guess the main uses for the ground motion database are improving source characteristics of Australian earthquakes, like our moment magnitudes, our stress parameters, evaluating and developing ground motion models, and it's also useful for engineering applications. And I guess we're also hoping that this data might be able to supplement other ground motion databases for similar regions as well. But like most areas, even active tectonic regions, we are still missing a lot of data in the areas where we need it most. And I can indeed confirm that the RAM is okay. All right, so this is just a screenshot of our ground motion database. I'm not going to go through this in too much detail, but we are integrating a lot of the GEM HazardLib tools and calculating ground motion attenuation and comparing that with the ground motion data that we've recorded. So there's a neat little tool here that you can toggle between the different ground motion models, different response spectral periods and so on, and look at your ground motion residuals. So as a first order tool, this is useful for end users to determine what ground motion models work well in specific regions. Yeah. Something that I've been doing a little more recently is looking at, do the source characteristics of earthquakes in Australia vary around the continent? And I guess what I'm starting to think now is that the hazard is going to be more influenced by the source characteristics and source variability of earthquakes rather than the attenuation itself. Because I'm seeing quite a large variation of things like stress drop, which affects the high frequency ground motions. So this plot, and that's going to be soon published in BSSA, is looking at clustering of different source characteristics across the continent. So using this clustering, what I did is I used a two-sample t-test to assess the null hypothesis, which is that the means of the stress drops within those clusters are equal. And so this matrix is, there's a lot of information in there, so I'm not going to go into too much detail, but effectively the green colors there show p-values greater than 0.05, indicating that the null hypothesis cannot be rejected, and the purple colors are showing that the p-values are less than 0.05, where the samples can effectively be treated independently. So one thing to point out here is this cluster 8, which is the Northwest Shelf area, is looking like an area that may be regionally different to anywhere else in Australia, effectively. And that's not surprising because a lot of the earthquakes there have very high stress drops. They're very high frequency energy. By contrast, this is the Yilgarn Craton here, this polygon. These are some of the oldest rocks on Earth. Now, traditional notions would have suggested high accelerations, low attenuation, but what we see is the earthquakes in this area are all super shallow, they're all super low stress drop. And interestingly, that's cluster 1. Interestingly, the area that they're most consistent with is this cluster 4 in Eastern Australia, which is some of our youngest crust. So go figure. These are considerations that we're going to have to look at more carefully as we look to develop our next national hazard model. Okay, so just touching quickly on our 2023 model. So it was intended to be a small update from 2018, but ended up being a lot bigger, as they usually do. So some of the updates were updating the fault source model, revising the earthquake catalogue. The suite of source models that we used were the same. They were just updated with the different catalogue. And we revisited some of the ground motion models that we used based on the data that we had collected. And in the meantime, it also published a new model looking at the attenuation of ground motions that we get from far field earthquakes in the Banda Sea, which are felt extensively in northern Australia and do cause damage from time to time. We had a couple of workshops, firstly seeking feedback from our 2018 model, and then looked at the refinement and homogenisation of the earthquake catalogue as well. So again, I mentioned that was a big issue with some of the other seismologists within the country. And then we used structured expert elicitation to essentially define the logic tree weights, and also to determine which catalogue should we actually use. Should we use a moment magnitude catalogue? Should we use a local magnitude based catalogue? Or should we use a weighted branch of both? And happily, most people finally selected that we should be using a moment magnitude catalogue. And then, of course, we had an international external peer review, of which there's a few people in this room today that participated in that. Okay, so the final results, just looking at the ratio. So this is a small map of the 2023, divide that by the 2018 model, and these are the differences. So we're seeing overall slight increase, and that's largely due to different choices of ground motion models. In the north, this is due to the new ground motion model that was developed for Banda Sea earthquakes. And then there was different treatment of how we treat the aftershocks from these long-lasting aftershock sequences. So I mentioned Tennant Creek. We had a magnitude 4 there just a couple of weeks ago. These earthquakes occurred in 1988. So these are long-lived earthquake sequences, and if you're wanting to go and build a structure there today, you need to consider that ongoing hazard. Okay, so some of the ongoing challenges that we have are around the earthquake geology. So the recurrence, frequency, magnitude distributions of our faults are poorly characterized. Are the earthquakes clustered on these faults? It's difficult to know with the long-term record. But we also have a prevalence of what we call one-off ruptures. So ruptures in our cratonic crust that when they're trenched, we can only identify a single rupture on that fault. And there is bedrock in the footwall, which is not necessarily expected. Earthquake catalogue, there's still a lot of work to do to homogenize the earthquake catalogue. One thing that I've been looking at recently is whether the B values of our earthquakes are spatially variable as well. And so that's something that I'd like to explore in the future. Ground motion, so I've already noted we have a sparse network and limited data to assess models particularly at the higher magnitudes and shorter distances. So based on the work that I've been doing recently, I think there is scope for us to look at developing regionally variable backbone models that we can certainly apply to hazard assessments in the future. And then there's questions around the weighting of the different types of source models. So we have source models that are based on essentially the historical catalogue, smooth seismicity, through to broad area zone based that model uniform earthquake rates over very large areas. So how do you weight them depending on what target probability you're trying to go for a national seismic hazard model? Okay. All right, so last few slides, I'll talk about how we're trying to currently uplift the Australian Earthquake Loading Code, so the 1170.4, and get the new hazard information into that building code. So we're currently updating that code in 2 phases. The first phase was completed in 2024, and that was just to incorporate a few new earthquake design actions, so it's more on the engineering side. And the hazard design factors, so the Z value remained the same as it essentially was from the 2018 amendment to the code. So phase 2 of the update is we're proposing new Z values for continental Australia. Okay, so go through a bit of a picture of the comparison between the earthquake hazard estimation and earthquake design, or the Z value maps in the earthquake codes over time. So I've already mentioned the Meckering earthquake. So after the Meckering earthquake, the first earthquake design code was developed for Australia. That was the AS 2121. This code wasn't enforced, it was voluntary, and so there wasn't a lot of uptake to it. Okay, then in 1989, we had the Newcastle earthquake. And then I guess the seismologists and the earthquake engineers said, okay, we need to take earthquakes seriously in Australia. So then there was an initiative to kickstart the development of the AS 1170.4. Before that, Brian Gall and co. actually published the first probabilistic seismic hazard map of Australia. So this map was largely developed before both the Tennant Creek earthquakes and the Newcastle earthquake. But for the actual building code, what they did is they took the hazard contours of Gall, they added some conservative padding factors, extended the contours out. This was generally a manual process, and that's what went into the first Australian earthquake loading standard, the AS 1170.4, which was published in 1993. The code was updated in 2007, but the map stayed the same. We've had a couple of other earthquakes in between. Geoscience Australia was asked to update the map in 2012. The local seismologists thought that actually reduced the hazard too much, and so that wasn't incorporated into the update of the building code. Then in 2018, we were asked to update the hazard again, and the hazard became even lower. And so, of course, the basis for the hazard map didn't change in the building code, but what was done is that a minimum floor level of 0.08 G was put in there to allow for a minimum level of seismic resilience. 2021, the Woods Point earthquake, we were asked to update the hazard model again, and this is the map. That is going to go into the building code. So I guess for the rest of the talk, I'll talk about how we're getting from here to here. I think I'm running short on time, so I will just skip over that. Okay, so the process for generating the maps was effectively firstly to take the PGA map with a probability of exceedance of, a 1 in 1,500 annual exceedance probability, and then apply a factor of 2/3. Okay, so it turns out that 2/3 factor roughly aligns with what we know as the KP factor, or the probability factor, at a return period of 1,500 years. So that's that dashed line here. So these probability factors are effectively a scaling parameter as you decrease the probability level for earthquake design. But you can see that most of the probability factors for most Australian cities are much, much higher than what we actually use in the standard. Then there was a bit of a disconnect between the design spectrum for what's in the standard relative to the uniform hazard spectrum. So that's comparing the blue lines and the red lines. So to essentially bring this blue line down to closer to the red line, what was done is we multiplied the PGA by a factor of 0.7. So that reduced the hazard even further. And then so localities with a Z value effectively less than 0.08 were then assigned to zone 1. Between 0.08 and 0.1, they were assigned as 0.2, and then greater than 0.1, they were assigned as 0.3. Then there was other factors that went into the code, such as the engineers didn't like irregular contours, so they asked us to fit the irregular contours with regular shapes, and in this case, ellipses. So that was done to keep the engineers happy. And then another factor was the Adelaide Basin adjustment. So there was, based on all of the adjustments, the Adelaide city itself, which is located here, fell in below that 0.08 level, and that was a bit of a concern with many of the engineers in the committee, because we know that the basin on which it is sitting has very, very high amplifications, particularly at around about 1 second. So we artificially drew an additional contour around Adelaide so that it would be bumped up to its original Z value in the hazard. So this is effectively the map that's going into the building code relative to the probabilistic map itself. But we know it's not all about building codes itself, so there's a lot of other uses for these types of applications, and so this is the sort of thing that I'm trying to focus on for our future updates of the building code, of the National Hazard Model. So in terms of concluding remarks, there's still a lot of uncertainty with respect to seismic hazard in Australia. Nevertheless, we are gaining new insights through strategic paleoseismic trenching, ongoing catalogue remediation, ground motion work, and the development of the ground motion database. So, and I guess finally, the NSHA is being integrated into the new building code, though there is a significant degradation in the information that is going into that. Okay, finally, I just want to touch on the session that we are having at 7 o'clock today, which will be talking about the development of guidelines for national seismic hazard models. So there's a group of us that have been meeting relatively regularly to talk about this. And I guess the reason is that we feel like there's a lack of standardized information about how people should go about developing national seismic hazard assessment guidelines. And so I'll let you read the details, but yeah, we would like to see you all in this session at 7 o'clock this evening. Oh, sorry, 5 o'clock this evening. Okay, I'll wrap it up there.
Maybe you can take one quick question. It is easy.
Well, you ask up that. Wait, questions. So the first one was regarding how much you have the Adelaide.
Yep.
Thank you. Do you anticipate that in the next update to the national hazard model that you will specifically target this using some sort of detailed adjustment terms in either the existing ground motion models or new ones for accounting for this, the basin effects here?
Yeah, I mean, it's clearly a pretty big gap. It's a large city, 1.2 or 1.5 million people. And so it is recognized as a big gap, and we can see that there are significant amplifications in the basin. So it is certainly something that I want to target for the future update. Yep.
Okay, thanks. And then my other question, maybe it's better to discuss separately, but you said regarding how you had the most similar stress drops, where you had vastly different ages for the crust itself.
Yep.
And you said go figure, but do you have any do you have any hunches as to what could explain that, or have you interrogated it much yet? Or
I think it's source depth. So for all of these earthquakes, you see very large RG phases, which is, and I mean, because we have really poor locations in Australia because our network is so sparse. But we know that these earthquakes are unambiguously shallow because they've got RG phases. And so that's the main characteristic that I can determine between them.
okay, thank you.
Yeah.
Okay, thanks a lot.
Maybe the first thing to point out, if you're not familiar with this name here, we're now Earth Sciences New Zealand. We used to be GNS Science, but late last year we were taken inside the National Institute of Water and Atmosphere, plus the Met Service and a kind of a standard agencies all came together into a big mega agency. We'll see how that goes. So I'll talk a little bit about what we did in the past and why we're doing what we're doing, and kind of just focus on a couple of things for the future now. So just I like to start out with the slide and some of these kind of talks, just because every model gets used a little bit differently in every country around the world, and I think we're in the situation where we're a model that's kind of on the more heavily used end, kind of within New Zealand. It has a lot of influence across different industries, with main users being building code and the Natural Hazards Commission, which is our national earthquake insurance. And our last update was at the end of 2022, and that resulted in very significant changes, 2 to 3 time increases in hazard for most of the country. And those changes went finally through the building code processes late last year, so they're out there for use now. I will say they're not required. We can talk about that later over coffee if you want, but it went through the engineering processes, no problem, and it's there, and it's expected to be heavily used. So in theory, we're indefinitely funded, but we're definitely funded until mid-June, and we're funded through our building code agency, kind of alongside the Natural Hazards Commission. So we're supposed to meet the needs of those two agencies, but we're supposed to be open to kind of all needs of the model. And the reason we really need to do this is we'd made significant changes in 2022, but as Celine was just saying, it was all done very, very quickly, and we couldn't do everything that we needed to do. And plus, we've just identified other things within that processes that we wanted to do. A lot of end user needs have kind of come up since that time, and also we trying to anticipate future needs of users by working with them, and we just science changes. It's been a while actually since we did this model now, so we need to keep up. So we're headed, where we're headed now is we're aiming for 2 different models. In 2028, we'll have a time-dependent, I say 1 year forecast in quotes, because I think there's still some openness on what exactly this time period is for this one. This is primarily aimed at New Zealand's Natural Hazards Commission for their reinsurance purchasing. Hopefully there'll be some other uses for it out there. It'll certainly be used in other contexts within New Zealand, and ultimately we're aiming to update that yearly. Hopefully we'll get to that straight away. And then in 2030 will be the next building code update, and that's in the same context of our current one, which is a time-dependent 100-year forecast, and we think we're looking at kind of regular 6-yearly updates on the NSHM in that context. So kind of where are we headed with kind of, given that we've got these constraints around it, what are we really trying to do? And there's this term best available science in the time allowed that gets used. I think I've never come up with a better term. I don't know what the right way to say this is. Hopefully we can, as a community, figure out a better way to say that. But it's really the community view of the best science in the context of the project and its uses. So that's our overriding kind of goal where we're headed. All science needs to be critically reviewed and defensible. And I think this one's super important, and I'm not sure it's one where we've done such a good job of as a community in the last decades. And I say balancing rapid pace of advancement of science, and I probably shouldn't have put rapid in there. I think just balancing the advancement of science with the need for robust science and kind of the stability side of things. And I'd say just in my mind, it's a little bit disappointing that in 60 years, there's some kind of basic things about the way we do PSHA that haven't changed, even though the rest of the science world has moved on. So I think we can do better about that. So we need to be driven and motivated by science, so reflecting our best science, but to answer questions that people actually care about. But I think that also includes the science community in that. But ultimately, we really want to lead to better decision making, so that means we should be improving things and we shouldn't be staying static. Okay, now to move on, I just wanted to put a couple of definitions out there before I go into the rest of it. This one may be super simple to most people in the room, but it's one I see people get wrong all the time, including within the hazard community, and people confuse it. And that's just what is the forecast time window? So when we talk about the forecast time window, that's the time period for which an expected number of events are calculated. So in PSHA or seismic hazard context, that's usually assumed to be some nominally long-term or time-independent rate that's maybe expressed as an annual rate that's constant in time. And in New Zealand, it's specifically for the next 100 years, so from 2023 on. And the reason we went that way was in New Zealand, there's no user that really needs a long-term forecast. It's being used for decisions that are on much shorter timeframes for that, so we really wanted to aim for that timeframe that's being used. So that's the forecast time window, so that's how many earthquakes are going to occur in this time. And the probability of exceedance is really nothing about time, and that people often get that confused with time. The probability of exceedance, say 10% POE in 50 years, that's purely just an expression of probability based on the forecast time window that you're using. And it's an important thing to get right, and it's one that it's poor. The use of POE in this 10% in 50 years, I think, is just a poor choice that we need to move away from. So when we discuss time dependence, we're only talking about the forecast time window. It doesn't affect it'll affect what your POEs that you get are, but it's not related to the time that's used for that. And hopefully that made some sense. I didn't do a good job there. And the next one is clustering and non-stationarity. And these are two different things. I'm being very simplified in what I'm saying here, but clustering is the variability around a mean rate through time, and non-stationarity are changes in the mean rate through time. So if we look at this little graph down here, we've got our mean rate here. If we're talking about a stationary process, then we'd see a mean rate that's constant through time, but we might see some variability around that as things happen. And that's the typical assumption in what PSHA, how it's done, that we think things work that way. We'll talk about a non-stationary process. You can see you've got a monotonically increasing mean rate as we go through time, but you see some variability around that. And this assumption of stationarity is really just that. It's an assumption. We don't have good evidence to support that. We do have good evidence that in the extremes there is non-stationarity. So regardless of what's right, there is uncertainty around this question that I think we need to be considering when we do our NSHMs. And we did that in our 2022 model. So we looked at these questions of how well do we know the mean rate. So that was some of the stuff that Celine was talking about, or really is there a mean rate is the additional question. So this is looking at some hazard curves from just a single location. Nothing special about this location. So this cluster of curves in the center, these different colors here, this is really referring to kind of the uncertainty in the Gutenberg-Richter parameters that Celine was talking about. And then if you look at the cluster of curves up and down, that's when we start to look at the non-stationarity, or the variability in the mean rate. How does it change through time? How well can we actually estimate that? And you can see that's quite significant. If you pick any particular intensity measure, you can see orders of magnitude differences across the POE for that. And for us in the New Zealand NSHM, it turned out to be kind of our largest source of uncertainty coming from the source side of things, and in some ways on par with what was being estimated from the ground motion modeling. So this uncertainty is driven by kind of multiple challenges. There's uncertainty across observations, so that's just what I'm kind of referring to down here. So that's earthquake geology slip rates, earthquake timings, geodetic strain, deformation rates, and so on, all that. Each one of those is taking a different snapshot in time and different processes and whatever, and there's uncertainty around what we actually know about the future from that. The next one is within data set uncertainty. And so if we look at this figure down here on the bottom right, this it's hard to read here, but this is the distribution of geologic slip rate data sample times. So this is starting age in kiloyears before the present, and that's a log scale going across multiple orders of magnitude here. So that's saying that's what time frame this particular data sample was taken from. And you can see there's huge variability in that, and that's just looking at the time samples. You start to look at spatial samples along faults, and there's a whole lot of assumptions that are going into all the slip rate data that we're using that tend to get just kind of washed away and forgotten about and put into maybe some sort of best estimate slip rate for a region. But ultimately, I mean, kind of it's really coming down to small number. What we have are small numbers of almost certainly biased observations from limited time windows. And really all these observations can tell us about are the time period that we took them from. Anything that we're doing beyond that is extrapolation. So I talk a lot about uncertainty. People aren't always sure that it matters. I sometimes question myself. But one thing we looked at in the New Zealand Building Code Committee was how does the uncertainty from the 2022 model from the epistemic uncertainty and the hazard compare to what would be reasonable estimates of the engineering uncertainty. So messy slide, but just focus on my two little red circles there. On the bottom left here, we're looking at the impact of the annual individual fatality risk from the epistemic uncertainty only from the hazard. So here you see the 90% confidence bounds on that. And then up here, these are very subjective uncertainties on the engineering side, but this is what came from the engineering members on the Building Code Committee they knew what we were trying to do here, so trying to estimate a reasonable uncertainty on that. And you can see they're not exactly the same, but they're pretty close. And I mean, this is a fairly arm-wavy type of exercise, but I think the take-home for me from this is that we're not looking at a different university of uncertainty on this, and we can't just kind of sweep this away and forget about it, that if we propagate these uncertainties through, they can be significant and they matter. But in the end, do we really care? And in my mind, that's certainly yes, we should care, that everything ultimately that the NSHM is being used for is some sort of risk-based decision-making. And I know there's been lots of literature out around discussions of using the mean or whatever for risk decisions and so on. But for me, it's fairly much convinced myself, and I think ISO 31000 really helps us here in how it defines risk, and that's the impact of uncertainty on one's objectives. So in other words, if we're not including these uncertainty into our risk-based decision-making, then we're not really ever going to know if we're meeting our risk targets as a country. And if we're just looking at the mean and we're not looking at what kind of happens when you get out into the tails, you don't know the impact, so you don't know what's going to happen. So I think it's really important that we think about this if we really want to start moving towards risk-based decision-making, which we're trying to in New Zealand. This last point's a little bit different, but related, and that's we've got different users that have different needs in terms of level of precision and level of detail and so on, and we need to make sure that we're meeting the users that have this higher level of need. And there's lots of discussion around complexity models in the literature and things potentially getting too complex, and there's some good philosophical arguments about being parsimonious with your model building that are pretty compelling. But I think it's important that we don't confuse complexity with uncertainty. And if we don't include the uncertainty, not only these reasons here, but we can't test our models. That's fairly intuitive that we don't know the uncertainty. We can't really get a legitimate test of it. But I think there's been a lot of work done in CSEP that has demonstrated this clearly, that if you don't include this uncertainty in your test models, you're getting kind of bogus results out of that. So to really understand how our models are doing, we need to make sure we're getting legitimate estimates of that uncertainty. Okay, I'm taking a long time here. In my mind, given all of that, the most impactful changes in the source modeling are likely to come from addressing non-stationarity and clustering. So what we've done in the 2022 model, we did have a lot of time dependence in there. We had the 100-year forecast framework. We had this uncertainty in the mean rate that I showed in the hazard curves. We weighted our different data sets differently, subjectively, based on kind of that slide I showed about what's affecting the non-stationarity and so on. And our total rate is a non-declustered rate. On the inversion fault model side, this was overly simplistic because we ran out of time at the end. We used a single BPT model, so in the next version, we're looking at using kind of multiple models on how we do that, back to the way we've done things in the past. But these total rates that come from the inversion model are then constrained by these multiple different data sets that we've got that represent different time periods. And so current work that we're doing is including multiple things, but one of the important things that we're doing is looking at how that variability that I showed across, say, the slip rate data set, how do we get that through the process? How do we better model that? And we go back to we're going back to the very starting points of those publications in the slip rate data, trying to understand better what's represented, because it's not, we call it data, but that's a model. I think Richard referred to that yesterday. I think it was a painting maybe, and that's a very good point. I mean, a lot of this, what we call data that we use for PSHA is not data, they're models, and so we're building models on models. So the other one is distributed seismicity model. So we use basically declustered, but then we added clusterings back in using the EPAS model, which I won't go into today. Then we did use uniform rate zones for lower seismicity regions, and for that we used a negative binomial model to account for variability that's much greater than Poisson, and I'll talk about that in a second. And so current work includes including aftershock clustering models, ETAS models, plus kind of conditional aftershocks, and we haven't figured out where we're going there with that. I just wanted to show this slide. This was work done by Pablo as part of NSHM, but other people have published on this in the last couple of years. But I think it's important to show this because the impact of clustering, of short-term clustering, or negative binomial and so on hazard is not always intuitive as a first glance. And sorry, this slide's a bit complicated, but the main thing to look at is really look at the red line here. That's our typical Poisson assumption. And then if you look at these two lines, those are the ones to compare it to these here. Those show if you start to account for the clustering in the hazard, what it's actually doing is it's tending, particularly at high probability levels, it's bringing down the hazard. And that comes, when you start to think about it, it starts to become a bit more intuitive, that when you're doing a Poisson model, you're saying, okay, there's going to be one earthquake every year, or whatever it is, and it's always the same. But when you start to account for the clustering, you're going to have some years that have 0, and you're going to have some years that have 100, or whatever it is. So you've got a much greater chance of having these years, or whatever your time frame is, that have lower rates in them, so that's then reflecting ultimately in lower hazard. And part of the problem with that is that the way we do things in hazard, we're looking at Poisson probabilities of 1 or more. So we're not actually looking at the effect of more earthquakes. We're not counting that into the hazard. We have implemented, Pablo, again, implemented into OpenQuake the ability to do negative binomial calculations that do account for 1 or more, 2 or more, 3 or more, 4 or more. But I have to say we haven't got our head around really how we'd use that right yet. So as I mentioned, we're headed for the New Zealand's Natural Hazards Commission, where they buy their reinsurance on 1-year cycles. We're looking at this nominally 1-year forecast, or 100-year forecast misinformation that would be changing on a 1-year cycle. So we're trying to get that in there, and we want to do that within the framework that we're using for the 100 years, so we can be seamless across all timeframes. And we'll have to use this model for different things in response and so on. And this isn't new to us. This is something that we've done a lot in the last 15 years. We did this in response to the Canterbury and the Kaikoura earthquake sequences, so we'll be using largely the same framework that we did for that. So largely based on a group of ETAS models plus the EPAS model that I mentioned before. So we're currently now going through what we call a testing phase on the ETAS models. So we've done this in the past, but there's million papers on ETAS in the last decade. So we want to take some of the new models that have come out and have a look at those and see if there's any significant changes that we need to be including. So we're currently going through getting the testing going. I think it's underway now while I'm away. And then we don't know until we see the testing results, but it's probably going to be something on the order of 3 different ETAS models that will combine to kind of try to capture what's going on across that range of models. So now into the negative binomials things. So the clustering, with the clustering models, you're actually adding them specifically in there with a model, but when we go to negative binomial, you're getting clustering in just based on the distribution that we're using. Again, this is work from Pablo, a slightly complicated slide again, sorry. So the way to look at this one is in one, you say go grab 10 events from the catalog, you look at how long that took to occur, that was 6 months, and then you grab the next exactly equivalent time frame, 6 months, and you count how many earthquakes are in there and say there are 4. And then you stack all those up. You do that many times in the catalog, and you get a distribution that looks like this. And the important thing is, if you look at the Poisson assumption, that's just this little red band here. That's the 97% confidence bounds on Poisson, which is fairly narrow. And if you look at the empirical distribution, we did this for multiple countries around the world. New Zealand, Japan kind of observed this, or see this the strongest, but you see orders of magnitude greater in the variability. Now, I will say this is on a non-declustered catalog, and we've gone through some arguments on why we do that, which I think I'm convinced about. But you still see something similar to this when you're looking at declustered catalogs, because declustering is an art. So the next step then is to look a bit more in detail on this, and this is kind of then relating it back to the non-stationarity ideas, and it's something we don't have our head around as well yet. So this is looking at the mean of that N2. So that's the second time period. So we count 10 events, and we look at the mean of how many events occur after every 10 event time period. And sorry, I cut off the axis or the labels here, I just realized. So we're looking at the mean for, this is two different locations. One of these is Japan and one of these is New Zealand. I think this is Japan and this is New Zealand. Maybe that's backwards. So this is looking the mean of the rate in the next time period. And what you might notice is if you have 10 events, you kind of would expect that your next period would also have 10 events as the mean. And that would be just the one-to-one line here, which is the dashed line here. So we see this bias high in the next time period. So we're seeing on average more events in the next time period than you see in the time period when you're in. And when we first saw that, we're like, what? We don't understand. We still don't completely understand it yet, but you would get this from non-stationarity. It could result in the same thing. I'm not sure that we could really argue that this is 100% because of non-stationarity, but it's real. I think we've convinced ourselves it's nothing, it's no mistakes we're making anywhere, it's no artifacts, it's really what's happening. We just need to get our heads around why it's actually there. But we do put this, when we put this into the model, it increases the hazard in those regions because you're basically saying you're gonna have a higher rate, and then we've calculated in this all with the negative binomial calculations. Okay, so just the last couple of slides here, kind of changing a little bit, but I think it's pretty related. And that's the kind of a testing phase that we put through all of the working groups that we're using within the NSHM. And so basically what we're trying to do with this is using all the evidence that we can, how you ever define that, to help us understand and provide us confidence in what's wrong and what's useful in the context of the NSHM and its uses. And there's just a whole bunch of people down here that have influenced what we're doing. I think we all miss Dave Jackson. He was one of the greats in the NSHM community for pushing these ideas. But Thomas Kuhn was, I think, a super important one. If you're not familiar with him, I'd say super important in the context of us, I think. And he's really the one that started bringing up the ideas of people have a big influence on science. And given the state of our science, and I would say relatively immature, and the amount of influence that everybody who's doing the science has on it, the number of subjective decisions that we've going on, has a big impact on what we do. And it's something as a community we don't think about enough, I don't think. So we use this hierarchy, this testing framework for the NSHM, and basically the idea here, I won't go through the details, don't worry. Basically the idea here is every decision, every kind of model that we're building or assumption we're making, we want to make sure it's passing somewhere through this triangle. So at the bottom, we've got very informal kind of discussion processes through the kind of very rigorous CSEP style testing or whatever it might be at the top. So we're really wanting to make sure that everything that we're doing, that we're challenging ourselves, we've got people from outside the team challenging us on what we're doing, and that we can, trying to get at our best model that we can, our best science in the end. So we're always trying to be cognizant of this triangle when we're doing things. And I think we did this a lot in 2022, and I think we're doing a better job of it now. So the last one is really getting them back to the Thomas Kuhn ideas there, and it's something that we have been doing for many years now in New Zealand, and that's we've got so many subjective decisions in the model. People are always part of the scientific process, and they always influence the results, and it's important that we're thinking about the processes around that to minimize the biases that are coming from that as much as possible. And an important one, which again I don't think we're doing as good a job as we can as a community, is who are the team members? Who is an expert, and how you define that? And I think there's a lot of literature that would suggest it's not always what we might typically have thought it was in the past. An important part of that comes down to this term cognitive diversity. If you're not familiar with that, I suggest you look it up and read about it because it's super interesting. But it really comes down to everybody's got different tools and different ways they approach a problem. They might even identify a different problem, but then they'll come to a slightly different solution, which is still a completely legitimate solution to that problem. And it's all within the epistemic uncertainty that we need to explore. So that's something that we're very cognizant of when everything that we kind of set up within the NSHM. Okay, so my last slide, just kind of quick summary of my conclusions. In New Zealand, there's no real users that need a long-term forecast. They've got very much shorter term, maybe up to 100, 200 years in some cases, that they need. They may need very low probability forecasts, but they don't need long-term forecasts. Two different things, as I pointed out. Source model uncertainty has often been assumed and stated quite strongly that it's inconsequential compared to ground motion uncertainty, and that's because it gets stripped away, and we just say it's all Poisson. Forget about it. That means, so you're forgetting about the uncertainty, and then you're saying the uncertainty doesn't matter. So it's a bit backwards there. From my perspective, understanding risk, uncertainty is important, clustering important, and almost certainly non-stationarity is important. So I think we can do, it's one thing we're focused on, and we're trying to do a better job of that. So that's it. Thank you.
Matt, thank you very much. I'll go back to the cognitive bias. How can you tell us how successful were you to remove the cognitive bias in the process, or what is the experience over there on the process?
Whether or not we removed it, I don't know if I can, how would you answer that? Or how would you know? That's a good question. I mean, I can say we did put significant effort into the processes and time and invested in thinking about it to set these processes up and following them carefully. So based on what's understood about bias, we've done a significant amount of work to try to minimize that. And I think we've operated a little bit differently than some other equivalent projects might work. So I'm optimistic that we've done a good job of capturing a bigger appropriate range of uncertainty and not having that as biased, but good.
So reduced is the wrong word here.
Yeah.
It should just be assess the range.
Yeah.
Thank you.
Of course, you've been putting a lot of focus on time, and so stationarity and clustering. What about space? Because what you were showing is also something that, of course, can be transferred from time to space. And there's probably an interplay between the two, right? Have you been thinking about that? How to address that?
Not sure I
So
complete.
for example, when I've been showing that scheme that was explaining stationarity and clustering, there are areas in which that could be applied in the way in which we are modeling seismicity in space. For example, if you take the seismicity in the back arc, in addition to the clustering, you could also use a trend that is decaying as you move away from the subduction. This is not something that in general it's easy to incorporate in a traditional smoothing algorithm. So I was wondering if that was also something that you were trying to in some way investigate.
I haven't thought about it that way, so I'm not sure. I mean, possibly what we've done with the uniform rate zones is somewhat getting at that. So that was acknowledging that when you have smaller sample sizes, you don't know. So you need to simplify the spatial assumptions.
Yeah.
And with the
No, my point is that, of course we can model the seismicity using an area source, but in that case you will have a trend that is almost uniform in space. The alternative is, of course, smoothing, but that will capture a wavelength that is probably too narrow in order to take a trend that instead you see it's a decreasing space, and it's a bit more difficult to capture probably with the two alternatives that so far we've been using.
So again, maybe it's not answering your question, but maybe. So our distributed seismicity model is very different than typical distributed seismicity models in that it's not a simple smooth seismicity model, that we take into account quite a bit of different geological information and so on. And some of that ends up being some of that smoothing, so you might smooth based on geological information and so on. So, yeah.
Any other? Rich?
What kind of ideas? What kind of ideas do you guys have for doing time dependence on faults?
At the simple end, it's combining multiple models, I guess, for the traditional one. I'm not sure that's the right way to go, but I don't know what else to do at that point. We're looking at some of your work in terms of how to handle some of the stuff I talked about in terms of the time sampling, and Genevieve's kind of, you may have seen that, I can't remember, kind of recreated some of what you've done. So we're trying to.
I haven't seen it, but I'd love to.
Yeah.
Hopefully she did better than me.
Yeah, we're still trying to explore how we can better account for the poor quality of the slip rate data that's constraining it, and poor quality also mean the temporal variability in that. A lot of that may come down to we're already including the slip rate uncertainty within the inversion process, but that was very simplistically done. So getting better distributions on those slip rate uncertainties that include some of this temporal uncertainty and so on, and using that within the inversion process as kind of a key driver for what we're doing.
But the rates that are coming out of the inversion are still a time-independent rate, or are you guys, building something like a VPT or something else into,
No, it'll be time. It'll be VPT. We'll be scaling things, and based on at the end there'll be a time-dependent rate. Yeah.
Okay,
Yeah.
cool.
And the 2022 was the same as with that. Yeah.
Okay, thanks.
Any other questions? Okay, thanks a lot, Mac.
My name is Asako Iwaki from NID Japan. So the National Seismic Hazard Maps for Japan, it was first released in 2005 by the Headquarters for Earthquake Research Promotion, which is called HERB, which is a governmental organization in Japan. And NSHM for Japan has two maps. One is the probabilistic seismic hazard map. Yeah. Okay, I found it. Okay, thank you. So one is the PSHM probabilistic seismic hazard map. That's the PSHA part. And the other one is the scenario shaking map for major active faults. And today I am going to talk about this PSHA map for the new 2025 model. And NSHM have been continuously updated and improved, adopting the new evaluation and research results. And our group, research group in NID, has been contributing to this, making these maps. So this is the outline of my presentation today. Well, the first part is the updates in NSHM for Japan 2025, which includes these major updates, including modeling of offshore active faults and updates in seismic activity model for Ryukyu Island, and major update in the occurrence probability for the Nankai Trough earthquakes, and updated velocity model in Tokai region, and finally the spectral acceleration hazard maps. And I will be also talking about our recent initiative in NID, that's the Ground Motion project in Japan, and I'm going to talk about the project outline and our outcome strong motion data platform, GPJ V1, and also the web application system, Japan Strong Motion Data Platform. So the first topic is for the NSHM 2025 update, and which is a modeling of offshore active faults in Sea of Japan. This is a brand new topic. So this update is based on the long-term evaluation by HERB for the offshore active faults in Sea of Japan. So this evaluation is based on the previous large-scale surveys and also incorporating new observation data. So this tectonic compression is generally in east-west to northwest to southwest direction. And so there are many strike slip faults in this western Japan, western region, and reverse faults in central region of Sea of Japan. So many damaging earthquakes have occurred in this region, including the 2024 Noto Hanto earthquake, that's magnitude 7.6 around here. So they incorporated the new observation data from the 2024 Noto Peninsula earthquake, and this evaluation of the active faults covers the region from western to central Japan only. So there is an open area in this northern part of Sea of Japan, and that's coming in the future. So these offshore active fault zones are modeled basically in the same manner as inland active fault zones. And the occurrence probability is calculated assuming a Poisson process using the average recurrence interval based on the slip rate given by the long-term evaluation by HERP, and the average displacement based on an empirical relation with respect to the fault length following Matsuda 1980 equation. And so these are the modeled faults. And these three segments are the Noto Peninsula Northern Coast Fault Zone. And these three segments are based on not the Poisson, but the BPT distribution, with the 2024 Noto Peninsula earthquake treated as the most recent event. So next topic is the update in seismic activity model for Ryukyu Island. So this is also based on the long-term evaluation by HERP for the seismic activities around Hyuga-Nada Sea and Ryukyu Islands. So the first of all, they incorporated a new Philippine Sea Plate geometry model. So and also the re-investigation of seismic activity, including the large historical earthquakes near the Ryukyu Islands. So first, I'm going to talk about the background earthquake with new zoning. So these are the new seismogenic zoning, and blue and 8 numbers shows the maximum magnitude for the background earthquakes for interplate and intraplate. So in this zone 6 along the Ryukyu Trench, and this is a very large zone, so the maximum magnitude is 8.5 for the interplate earthquakes. But although it's very large, but it has only small effects on PSHA. We confirmed. And also the maximum magnitude for intraplate is now as high as 8.0, and it is based on the re-investigation of the historical earthquake of 1911 Kikaijima earthquake with magnitude 8.0. So, and then next topic is the magnitude, the Hyuga-Nada earthquake in this area, zone 2. This is this area, Hyuga-Nada earthquake. Hyuga-Nada area is part of the possible rupture area of the Nankai Trough earthquakes, but it is also evaluated as a region where recurrence earthquakes can occur separately from the Nankai Trough multi-segment rupture. So both magnitude 8 class earthquakes and magnitude 7 recurring earthquakes are modeled separately from Nankai Trough earthquakes. And also there are many offshore active faults known to exist along this Ryukyu Islands, but the individual fault evaluation have not yet to be done, so it will be coming in the near future. Okay, so the next topic is the major update in modeling of Nankai Trough earthquakes. So it is based on the revised long-term evaluation of seismic activity model in Nankai Trough earthquakes that by HERP that was released last year. So one point for this long-term evaluation is that they consider the uncertainty in the observation data that represents the slip amount of the historical events, which is the estimates of the coseismic uplift at Murotsu port, which is located right here. So they consider the uncertainty in the measurement of the uplift. So the second point is is now they provide two different approaches, two different models to estimate the occurrence probability for the Nankai Trough earthquakes. One is called Slip Size Dependent BPT model, or SSDBPT, which incorporates event-to-event differences in slip amount. That's represented by the uplift measured here, into the conventional BPT model. And the other one is the BPT model that's based only on the earthquake recurrence intervals of the historical events. So in the document, in the revised long-term evaluation document, neither the SSD BPT nor BPT model can be scientifically preferred at present. So both probability estimates are retained. So that should be treated as the epistemic uncertainty in PSHA. So I'm going to try to explain briefly about the two models, SSD BPT and BPT model. So both these models are evaluated using Bayesian estimation. So the uncertainties in model parameters are propagated into the 30-year occurrence probability, that's P30. And so based on the to get the posterior distribution of P30. So based on this distribution for these each of the models, the 70% credible interval is reported as the probability range by the long-term evaluation by HERP. So when we implement this posterior distribution of P30 into PSHA, we did not directly sample the P30 from this distribution. Instead, we just used the representative value for the average case. We just took the mean value for this model and this model. And for the maximum case, we took the upper bound of the 70% credible interval, which is almost 100% here and about 50% for this model. So, and still the SSD BPT and BPT models are retained as a separate epistemic branches with 0.5 and 0.5 weights. So, but we are still thinking of an appropriate ways to, or appropriate and explainable ways to implement these epistemic branches into our PSHA map. And for the version 2025 and for the GEM Mosaic 2026, only the probability P30 for these two models are just simply averaged into, so that it's just only one branch. So the next topic is the updated velocity model in Tokai region. So Tokai region is in the central Japan, including the big city Nagoya and many major factories like Toyota. So there is a combined shallow and deep subsurface velocity model that's called SD model of Tokai region, has been newly constructed using many geophysical and geological data and microtremor and earthquake measurement by our colleague Senna-san. So VS30 distribution map based on the shallow and soil layer model is applied to this our 2025 NSHM. So this is the new VS30 model, and this is a comparison of the VS30 and it says current, but no, previous VS30. So it's quite a large difference. So, and not just the VS30, but also the deep subsurface velocity model is also updated. So this these two figures compares the new sedimentary layer model in whole Japan. So so this figure compares the previous version and the new version of the deep subsurface velocity at the depth of S-wave velocity of 1400 layer, or the 1400. Okay, the next topic is the release of spectral acceleration hazard maps. So this is a new product that was released last year, I think, last year. So this is a nationwide seismic hazard maps for spectral acceleration. So yeah, I'd like to mention that our PSHM maps are basically based on PGV and seismic intensity, Japanese seismic intensity. But now the hazard maps for spectral acceleration at multiple period and also PGA are available nationwide. And it is developed for engineering applications, including seismic design. So we are, if you visit this site, we are doing this user surveys. So in order to understand the current usage and guide future outputs that better meet diverse needs. So, and also currently, we are discussing with the engineering community of how this kind of spectral acceleration hazard maps can be used and how it can be improved to provide more, or meet more diverse needs. And so if you want visit this site, you can also click one mesh to get the uniform hazard spectra and also the hazard disaggregation. And this is the point near my house in Tsukuba. Full of danger. Okay. So this is the output, final output, the NSHMJ 2025. So this shows this, not the PGA, but the JMA seismic intensity for 6% exceedance in 30 years. And this figure shows the difference between 2025 and the previous version, 2020, that was implemented in the last GEM mosaic. So I'm going to explain some differences here. So here in Kyushu, the size hazard is higher because of the newly considered Hyuga and other earthquakes. And the most considerable change is this blue color along the Nankai Trough, which is caused by the change in the occurrence probability in Nankai Trough earthquake. This is the hazard has been lowered, but we are very careful about sending message to the society about the lowering the hazard. So we have to be very careful about how to communicate these results to the society. And some effects from the offshore active faults are shown near the Noto Peninsula. Not very easy to see from here, but yeah, and also for the Ryukyu Island seismic activity model. Okay, so I listed some remaining challenges in our NSHM framework. So one is to clarify how epistemic uncertainties should be represented across not just the Nankai Trough earthquake, but all the source models, including their possible implementation as logic tree branches. So we have now explicit two epistemic branches for the Nankai Trough earthquakes. So we are exploring, right now we are exploring more explicit representation of P30 in logic tree. So the next one is a systematic treatment of epistemic uncertainty in ground motion modeling by incorporating multiple GMMs. Currently, our NSHM basically uses one GMM for the PGV and map, and another GMM for the spectral acceleration maps. But we are trying to make more multiple GMMs. And we have just started this new project to make multiple GMMs. So I'm going to explain this later. And the third topic is to strengthen the bridge from NSHM to engineering application and risk-informed decision-making. So now that we have released our spectral acceleration hazard maps, our communication with the engineering community has been started. Okay, so now I'm going to talk about the ground motion model project in Japan. It's the GMMPJ, and that's our recent initiative that started in NID. So in order to consider epistemic uncertainty in Japan, GMMs based on common database are needed. So we have started this project to develop a framework to construct and utilize multiple GMMs based on common strong motion database. So this project has mainly two parts. One is to develop and analyze the GMMs by inviting many researchers from the community for GMM development for GMM analysis. And we called for the modelers for two categories. Category one is for GMMs that can be applied to nationwide NSHM. And the first result is coming this fiscal year, which is the end of March 2027. And the second category is for the GMMs for any other specific purposes or any other challenging initiative. And the results for this second category will come in the fiscal year 2027. So the second part of this project is the construction of strong motion database system. So we collected strong motion records from many observation networks in Japan and site and event metadata and velocity models into a database. And flat file GPJ v1, we have just finished making a flat file GPJ v1. And also, we have just released, last week, we have just released a web application system that's called Japan Strong Motion Data Platform that enables data processing and visualization and analysis for multiple observation networks in Japan. So I'm going to briefly introduce the flat file GPJ v1. So this data set includes the open access strong motion data from public institution in Japan, not just the NID, KNET, and GICNet, but also networks such as JMA and local government, Building Research Institute, Port and Airport Research Institute, and a Association for Earthquake Disaster Prevention or something. That's a collection of the strong motion records for the 1995 Kobe earthquake. That was, at that time, NID, KNET, and GICNet did not exist. So this is a very important collection from, not just from the public organization like universities, but also the private companies. So we incorporated these records into and like harmonized them into a flat file. So this shows the number of the data for each organization. NID has, of course, a lot of huge number, but other organization has very important events, such as for example, JMA has a very spatial resolution is very high, so it has a very important near fault strong motion data for magnitude 7 earthquakes, 6 and 7 class earthquakes. And BRI and PARI, their history is very, very long compared to NID, so they have a lot of important earthquake records in 1970s and 80s. So, okay, I don't think I have, okay. So this is the classification of earthquake type determined based on the plate boundary geometry and focal mechanisms. And we have classified into 5 types, so the crustal earthquakes and interplate earthquakes on the Pacific Sea Plate and the intraplate on Pacific Sea Plate and interplate on Philippine Sea Plate and intraplate on the Philippine Sea Plate. And this is the distribution of the VS30 for different observation networks. This VS30 is assigned to each site according to the following order of priority. The first is the measured VS30 from VS profile if it's available. And the second one is if the VS profile is not deep enough, if say between like 10 meters or to less than 30 meters, then it's estimated from the shallow VS profile by the empirical law. And the third one is the estimated not from the VS profile, but from microtumor measurement. And also, Japan, we have just released Japan Strong Motion Data Platform last week. And users can search for and download data via the web. And the concept is to use the strong motion data and search for the strong motion data for multiple observation networks. But currently, it's just a beta version, so it has only KNet and GeekNet data only. But ongoing work is we are now implementing JMA and local government data also. So in summary, NSHM Japan Model 2025 has been implemented in GEM Mosaic, and it includes the following updates, these updates, and future and ongoing issues. First is the treatment of epistemic uncertainty in source and ground motion models. And our ongoing initiative is called the Ground Motion Project in Japan. And we have just released the web application system, Japan Strong Motion Data Platform. Okay, that's the end of my presentation. Thank you very much for your attention. Actually, it's not real time. First of all, it's publicly available, yes. And this is not a real time data system, but we have the database, the static database of the strong motion data, big data, and you can search for the data by the metadata and also the strong motion intensity. Yes, past events, yeah, yes, that's right, yes.
Thanks, Asako. So you said that you were classifying the events in your new flat file into broadly, for specifically the subduction, the Philippine and the Pacific subduction arcs. And I just have a question about the existing GMM. You have these sort of location-based adjustments within this single Morikawa 2013 model. Do you anticipate in these new national seismic hazard model scale GMMs that you will have distinct ground motion models for dealing with each of those sort of, in effect, tectonic regions or like source localities? Or will you anticipate a similar behavior to in the existing model where you have maybe this is better to ask afterwards, but I was just curious if you know anything about that, because it's like an interesting feature of the existing model, how it works. Yes, sorry. I was just curious if you had any insight on the development of the new models, if they're working in a similar way to the existing model, or they'll be split up into more distinct models, basically.
What's the point?
So your model has the Morikawa has some regional adjustments, right?
Yes.
So Chris is asking if you will maintain that approach, or you are thinking two completely different models, maybe separated into a model for a certain region, another model for another region.
Okay. Basically, of course, it depends on the modelers. But for example, for Morikawa Fujiwara model, within his model, he classifies the many earthquake types. So it depends. Because we are trying to make multiple GMMs with different approaches, so it's okay to have one GMMs for specific tectonic condition or one GMM for different types of earthquakes.
Okay, thank you.
Okay.
Yeah, we take the last question from Trevor.
Okay. Okay, I think my question's a little easier. So you mentioned the decrease in the hazard in the Nankai Trough, and you're being careful to communicate that information to society.
Yeah.
I'm wondering, how has the communication with the engineering community been?
Okay, this is very difficult, and actually our public release of this 2025 model is pending. So GeoMosaic is the first map that can be seen. So actually, and to answer your question, though, it's not just the engineering problem, but also political issues. Yes, because it has a huge impact to the society, the Nankai Trough earthquake. Yes. Maybe, I don't know if that answers your question, but yes.
Very good. Okay, thank you very much.
Thank you.
So we're in the U.S. We're sort of in between major updates. We had a 50-state update in 2023, and our next one is in 2029. So I was thinking about what I would present here today, and I decided to talk really to kind of follow these points here. So Trevor mentioned the guidelines for national seismic hazard model programs, and you're going to hear more about that from Delphine. I essentially pulled the draft chapters from that report, and I'm kind of just spend a few minutes on each of these as it pertains to the USGS National Seismic Hazard Model. Okay. So I won't read through all these now. I'll just get started. We can start on the motivations for the NSHM. So I can kind of see this. So I'll go back to the original motivation and mention that at least this paper by Alan Cornell on what we now call probabilistic seismic hazard analysis was really thinking about the engineering design of buildings and other structures and how we get to that. So I think I've highlighted here a few of the aspects that refer to that. So Alan Cornell was my PhD advisor, so that's definitely rubbed off on me. So really for USGS, the main motivations, we classify them into the building code side, right, which was part of the original motivation. Lots of different building code documents. One, for example, that's really for buildings in particular are these NEHRP recommended seismic provisions for new buildings and other structures. I'll talk about some of the other building code documents. And then we also have motivation to develop our models for risk modeling purposes, whether it's insurance or in this case, this is a FEMA document that Kishore Jaiswal, who's at the conference this week, leads in collaboration with the Federal Emergency Management Agency. So we tend to spend a lot of time on building codes because in the US, the building code process is a volunteer process mostly. And so it's something that we as government employees feel like we need to really feed into. But we obviously have risk assessment needs as a country, and even the insurance modeling industry, while it's for profit, I think our work plays a role there. I will also mention that on the building code side, right, the building code, they tend to be more of users of outputs from the NSHM, whereas I think on the risk modeling side, you have a bit of both, but say in the insurance modeling industry, really a lot of the inputs or components of our model is what is handed off, right? Okay, so that's our main motivations, the bodies involved. So users, funders, advisors, implementers, reviewers. And so I'll go through these categories. So main users on the building code side, on the left side, it's primarily this National Institute of Building Sciences, Building Seismic Safety Council, NEHR Provisions Update Committee. Lots of acronyms there. And they're the ones that develop those NEHR provisions that then eventually become U.S. building codes. So just recently, and I just got this email a few days ago, the California Earthquake Authority has within it a Best Available Science Committee, and that committee is really putting together this advisory committee on earthquake risk modeling. So their idea there is to organize, I think, the risk modeling community in a somewhat of analogous way to how the building code community is organized by at NIMS, BSSE, and their PUC. So these are two main users that we're interacting with. I'll go just aside on the building code side, some of the main documents, and that building code side is really what dictates our schedule. So we coordinate with a 3-year update cycle of it's called the International Building Code. It's kind of like the World Series of baseball. It's really just US, but they have a 3-year cycle, and we match that cycle. And so in particular, I'll say, like, for example, the next International Building Code and some other related documents is in 2030. We also feed into the American Society of Civil Engineers documents. So there are 2 documents, one for retrofitting existing buildings, one for designing new buildings. So that's a 2028, 2029. And then, as I mentioned, the NEHR recommended provisions, which is focused on seismic and feeds into those documents above. And then it's these USGS National Seismic Hazard Models, the 2025 Puerto Rico and US Virgin Islands, and the 2023 50-state update that feed into those building code documents. There's lots of other building codes for different parts of the infrastructure. For just a couple of more examples, this American Association of State Highway and Transportation Officials, AASHTO, so they really look at bridge design, and then American Railway Engineering and Maintenance of Way Association. They also look at bridges, but for railways in particular, as well as just the rails themselves. Okay, so funders, really we're fortunate in the US. There's a National Earthquake Hazards Reduction Program that's funded by the government via the USGS Earthquake Hazards Program. And so one thing maybe on the initial slide, we call our National Seismic Hazard Model a project, not a program. Maybe we could change that, but there's lots of other programs like NEHRP and the Earthquake Hazards Program that take that name. I'll mention recently for the 2023 NSHM, there was a congressional plus-up that was about $1.3 million per year was provided in order to update Alaska and Hawaii with the coterminous US or the other 48 states. So previously we had updated the 48 states pretty regularly, but Alaska and Hawaii we just did when we had time, which was not often, right? Then for Puerto Rico and the US Virgin Islands, the NSHM update, the clock was advanced. We were going to do it in 2026 in between our 50-state updates in 2023 and 2029. But because of the recent earthquakes in Puerto Rico, the clock was advanced on that, and we got it done at the end of 2025. And so we got a little more funding to do that. There's also been some discussions or consideration of a plus-up for a fully national NSHM, where every time we would update all 50 states and the inhabited territories at once. So these 3 bullets here kind of describe that for us, the way we get more money is not the most interesting way you would think, right? It's not thinking about, right, improving how we quantify or propagate epistemic uncertainty. It's, hey, let's do all our regions on the same schedule, right? But it gets us the money to do the more interesting work, right? That more interesting work that we do have in the Earthquake Hazards Program Council, they have a 10-year strategy and some aspirations in there that relate to the NSHM are listed here. These aspirations mean we feel like we need additional funding really to tackle these well. And one's near real-time hazard forecasting, which has lots of, I know, engineering applications, but other as well. And cascading hazards that we've heard Jim is beginning to work on: liquefaction, fault displacements, landslides, and tsunamis. So those are things that we hope to get some additional funding to really dive into in the future. Okay, the advisors for us. So the USGS Earthquake Hazards Program has the Scientific Earthquake Studies Advisory Committee, CSAC, and a subcommittee of that is the NSHM Steering Committee for USGS. So we've had that for maybe 15 years or so now. But more recently, for 2023, we created 2 subcommittees of that, the ERF, our Earthquake Rupture Forecast Participatory Review Panel. So we just, seismic source characterization, we call it Earthquake Rupture Forecast at USGS, something that maybe is perhaps more generally understandable. And then we have a parallel ground motion characterization participatory review panel, right? So those are our advisors for our project. I'll note this because it becomes important for how we do things at USGS, at least, that these participatory review panels, you can kind of regard them as being in between co-authors. They do not end up as co-authors on our reports, but they're also not independent peer reviewers. We have separate independent peer reviewers, right? So in between those 2 things. All right, then on to the implementers. So probably hard to see this list, but this was the 2023 USGS 50-state NSHM and the list of co-authors there. Mostly USGS people, but some external people as well. So we collaborate with a broad group of people. And this is generally how we structure our project/program. We've got sort of the hazard integration component, a specific task for delivery of these NSHMs, whether it's to engineering or the broader public, the ERF development component. And then we do a lot of meetings and public workshops, so we actually separate that out, and the budget for that is something that we keep track of separately. The ground motion characterization is actually done within a separate but associated project at USGS, this ground motion project. We've got an earthquake geology project, and then an engineering and risk project where we interface a lot with building codes and risk modelers. And then lots of other people, like the people listed in that 2023 publication. All right, and then in terms of reviewers, in addition to the advisors that do serve as reviewers, but really participatory reviewers, we submit our papers to journals. We have a USGS internal review process that's additional peer review, supervisor review, center review, bureau review. We put our NSHM documentation out for public comment and get reviews in that way as well. And then this last bullet are user reviews from building code folks and risk modeling. Usually that's a type of review that comes a little later in the process, right? We've got a complete model, but I say that we definitely get review comments. And for example, I'll mention that we've changed our 2023 USGS hazard model, done a revision that was based on some questions that were asked by the building code committees. Okay, So framework, let me look at, so this one is the chapter that currently is sort of in the draft is set up for some of the more technical aspects, and I figured you'd be hearing plenty of that at this during this day in this workshop. So I won't really cover this except to say, right, that we have sort of the typical components that we use in building our model. So I'll skip that for now, but if there's time for questions, people are welcome to ask about that. So products and their applications. So I'm going to mention this, but products, we build these NSHMs for different parts of the U.S. and its territories. So Puerto Rico and the U.S. Virgin Islands was just completed, as I mentioned. Guam, we're now working on Guam and the Northern Mariana Islands, and American Samoa in the Pacific. So that's our current effort, and we're already starting to work on the 2029 update for the 50 United States. And you can see in the past updates here, again, we updated the coterminous US quite often, but the other states and territories not as often. Puerto Rico, we managed to squeak into those NEHR provisions for 2026, but all these other ones will go to the 2032 NEHR provisions. So it's a long lead time. Sometimes between our NSHM and it actually becoming building code, it takes 10 years, right? It's a very long process. Part of that I think is good because I think it brings some stability in terms of more time to review before things are really widely used. Okay, a couple notes on the 2023 50 state update. There are these interim revisions that have been developed, and they're in the process of being published. Peter Powers and others. A few relatively small things, a few with some significant impacts on values. And again, if anyone has a question, I'm happy to talk about those. And right now, we're developing a time-dependent version, a long-term time-dependent version that accounts for the time since the latest earthquakes, and that's Nedfield that's working on that now. All right, so those are generally the products. In terms of some of the delivery of those products, a lot of what we do is available through this USGS Earthquake Hazard Toolbox. So if you can even see in the back, right, we've got, I don't know if this is, yeah, you can get hazard curves dynamically, meaning the computation is done on the fly, or statically, meaning it's interpolated from pre-computed hazard curves. We've got a disaggregation tool available online, and then different ways to interrogate both the ground motion part and the earthquake rupture forecast or the source model part of our NSHM. Right? So those are the tools in the middle here. Even some of the National Crustal Model, those geophysical parameters are available, and then we start to get into building codes a little bit here, where we have a calculator for risk-targeted ground motions, which was what is used in a lot of applications in the US. All right, I will mention also that earthquake hazard toolbox is really for the hazard information. Once that's translated into building codes, at least for buildings, we have an arrangement where at USGS we create a web service, which is on the right here. It's sort of a pretty rudimentary web tool where you can enter a site class, a location, risk category information, and you get back in sort of a rough text form all the data or the values that correspond to that. That then feeds into a more user-friendly tool, the ASC hazard tool, on the left. And so we've got this arrangement where we don't have to spend all the time on the hazard tool, but we spend our time on the web service. And you'd be amazed like how much engineers will accept if they just have access to it, right? And so we develop our ground motions for building codes in a little more complicated way with risk targeting, and things change every time we do updates. But at the end of the day, people can get to these values in pretty simple and consistent ways. All right, chance of damaging shaking maps. So this is our ongoing attempt to create a product that's more user-friendly, right, or to the general public. And so for all the regions that we cover, we've started to map this chance of slight or greater damaging earthquake shaking. This particular map happens to have it in the next 100 years with different categories that I think are missing the percent signs here. But just as one map that, the media, for example, can use, this chance of damaging shaking map is sort of what we're trending towards, as opposed to showing a map of, say, 2% and 50-year ground motions that are a little harder to explain. So we're working on this map, and we constantly welcome feedback on it. Okay, model checking, quality assurance, and peer review. So for these parts of model checking, we'll say is something that, at least in terms of more rigorous testing, we haven't done a lot of. And so I think that's a growth area for us. There are a few examples here. Leah Soldic was a postdoc with us that looked at comparing our results to this historical intensity observations. And then at some point, I had an intern, and we looked at back when we had 1-year forecasts for induced seismicity from oil and gas, wastewater injection. We did some comparisons with instrumental data there as well. So kind of growth area for us, we certainly do plenty of, and like Matt, your triangle, right? Lots of review, lots of comparisons with past models, or in some cases with models, for example, from GEM. We do a lot of that and really try to dig into and understanding the changes from one update to another. That's important to relate to at least engineering users, if not others. But the testing side is something that we have lots of room to grow in. Okay, then quality assurance. So mostly our quality assurance, I think, would come from just the review process and the participatory review process, the independent peer review after it. But I thought I would mention here that we do use 2 different PSHA softwares. So they're both written in Java programming language. Right now, we need both of them because the earthquake rupture forecasts have been done in OpenSHA since 2014. And then on the ground motion side, we have hazard results and ground motion models back to 2007 in the NSHM PHAS. So we have sort of a combination of these 2 things. They are interoperable in the sense that OpenSHA, the ERFs can be passed to NSHM PHAS for calculations, and the NSHM PHAS ground motion models can be used by OpenSHA. But I think we benefit from the collaborations between the 2 codes. Certainly now we have Peter Powers, who works mostly on NSHM PHAS, and Kevin Milner, as well as Ned Field, that work on OpenSHA. And really by using both of these, we're engaging all those folks on the codes side of the problem, as well as external contributors to OpenSHA, for example, and not as many for NSHM PHAS. We saw this for 2025 Puerto Rico and U.S. Virgin Islands, that there we had the benefits of just really running things in 2 different codes and comparing them and making sure that they matched at least as well as we would expect. So I guess that's sort of part of our quality assurance, is those comparisons between what we get for different codes. All right, and then on the delivery of the NSHMs, so really that delivery side, the earthquake hazard toolbox is tied to NSHM PHAS right now, And so things funnel through that, but obviously OpenSHA could also be linked into our earthquake hazard toolbox. All right, quality assurance. And then peer review, again, I mentioned most of that, but one thing I thought I would mention is that our participatory review panels, which in effect we have 3, because we have the ERF, the ground motion characterization, and then our steering committee sort of serves as our hazard integration review panel. And so each of those review panels publishes reports on their reviews. And the way we're doing it now is that initially they'll publish a preprint so that we can get those reviews out quickly and we can reference them. But now those panels are interested in us publishing their reviews in a USGS scientific investigations report so that we are kind of permanently archiving those review reports. Okay, company documentation, these ones I'll speed up here. So journal publications, we've kind of gotten in the mode of essentially publishing an ERF overview, a ground motion characterization overview, and a hazard overview, and that triplet sort of being the description of the model with references to lots of companion papers. So these are examples that are probably hard to see, but they're all for Puerto Rico and the U.S. Virgin Islands, and so there were a dozen papers on that. So not looking forward to how many papers we're going to manage for 2029 50 state update. So we publish data releases. So USGS has its own data repository. So we put all the results and model components, in some cases, out on this USGS Sciencebase data repository. We've got software releases. So we publish the software really through GitLab, as you're seeing here. And then media guides. So for Puerto Rico, we developed this media guide, which was also translated into Spanish, although we weren't allowed to post the Spanish version on our website at this time. But this media guide, right, was something that we could talk to the more general public and via the media indirectly. All right. Okay, and lastly, the challenges and future direction. So lots of those, I think we're going to talk about those more at the end of the day, but I'll just use this as a chance to describe what our priorities are for the 2029 50 state update. So we're working on time-dependent earthquake forecasts, sort of the long-term time dependence, accounting for the time since the last big earthquakes on faults. We're working on that now, NetField's working on that now. We also want to include the shorter-term time dependence or the clustering aspect. We're not as sure whether we will get to that by 2029 or if it's going to be shortly after. NGA West 3 ground motion models are being developed, and a few of those are going to be published this year, which is sort of our deadline for using them. And so there's a bit of a push there. And some of those models, others would know more than me, but are including some partial non-ergodicity. Right. Then we're trying to harmonize across geographic and seismic tectonic regions. So this would help us if we can do a 50-state update plus the territories. If we're really doing things in a consistent way, we can do them all at the same time. I'm sure, right, something that Jem knows very, very well, right? So both on the ERF and the ground motion characterization side. The epistemic uncertainty improvements, both on the ERF and the ground motion characterization, we think we've made good steps forward on that, including for Puerto Rico, where it was the first time that on sort of a grid covering the islands, we did epistemic uncertainty calculations across that whole grid and tried to do a better job on our quantification and propagation there, but we still have more work to do there. Fractile hazard curves that come out of that, again, we're just starting to systematically produce that. And sometimes the results are surprising or interesting, right? And we learn a lot about what we're not yet doing there. Ground motion rupture directivity, I started at USGS in 2004, and I think even before then, people always ask, do you include rupture directivity? And ever since then, the answer has been, well, not explicitly, right? So we're trying to take a step forward there. It might still be in the research NSHM, mainly because of some of the issues between, how this is done for strike slip versus dipping faults. And then just other updates in general of the earthquake rupture forecast and the ground motion characterization. So that's our list for 2029. I'll just go back to that outline of the chapters in the draft guidelines. That's why it starts with number 2. It says chapter number 1 is the reasons for the guidelines, and I think we'll hear more about that from Delphine later. So, thank you.
Thank you, Nico. Very nice summary. Maybe we can take one quick question. Okay, I have one, very simple. You've been talking about quality assurance and you've been focusing on the code for calculating the hazard. Have you been also thinking about the codes that are used to build the various components of the model?
Yeah, I think one thing that we need to do, for example, like the statistical seismology part, they're integrating the codes. Now those codes are sort of separate from OpenSHA and NSHMP has. So integrating that into the whole software platform is something that's been discussed there to try to, I guess, get more eyes on it, a little more QA on that topic. So, yeah, I think, again, I think a lot of it comes from our review process and our interaction with the public, lots of public workshops on this, but I think we're finding that, yeah, the codes are an important part of that process as well. And, yeah, components, I think we've got room to grow there, yeah.
Thank you. Really.
All right, thank you.
So after integrate all of this catalog, and then we can get such kind of area source that cannot be, for those kind of seismicity activity that cannot be attributed to either active fault or subduction zone. We also have such kind of the contribution from our geologists or geomorphologists. Our group member from National Taiwan University, Bruce and Chen Hong, especially for Chen Hong now, he got his PhD degree and then recently working with us in National Central University. What they have done is to propose the first version of the offshore seismogenic structure, as you can see the figure to the left, that we identify, they identify the delineations of each of the structure, and furthermore, they propose each of the slip rate of each structure. As you can see the figure to the right, the different color shows the different slip rate of the structure. So as you can see, some of that with red line, which suggests that relatively higher slip rate, which suggests could result in some relatively higher hazard. So by integrating this, we further consider some kinds of the multiple fault rupture. That's such kind of the fault could have some link with other or neighboring fault that could result in even larger magnitude with higher ground shaking. By integrating all of this, then we can evaluate their impact on the seismic hazard. As I mentioned, considering the fault geometry with corresponding some of the active fault parameters, including slip rate as well as the maximum magnitude, then we can calculate the impact of the seismic hazard, as you can see the figure to the center or figure to the right, especially for the figure to the right, showing the impact of this offshore seismogenic structure. And you can see for some of the region, especially in the northern or southern western Taiwan, it shows a slightly higher hazard than those without this kind of structure, such kind of the impact is attributed to some of the existence of the offshore seismogenic structure. And furthermore, in the northern western Taiwan, you will also see some hotspot over there that can be associated with such kind of the multiple seismogenic structure rupture. One thing I would like to mention is for those red spot over there is our hometown, my hometown, as well as the science campus, which produce a lot of the computer chips and some others. So that means if we are talking about the seismic risk impact of the economy, we need to think about the impact from the offshore seismogenic structure. We not only propose the new generation of the seismogenic structure, we also update our inland seismogenic structure. So we have several innovations. One is we have several newly identified seismogenic structure in the southern western part of Taiwan. As you can see, in southern western part of Taiwan is I got it. In this region, you will see this region is quite busy in the active faults over here, which is some of the newly identified structure. Besides such kind of a newly identified active fault, we also propose a new model by considering the BPT model, which is a time-dependent model. That means we consider the time elapsed of the previous earthquake along each of the fault that we identified. So that means for some of the fault that has very long, relatively long elapsed time, for example, the Meishan fault it ruptured in the early of the 20th century. We expect the seismicity rate will be relatively higher than our expectation based on the time-independent model. And besides, we also consider such kind of the multiple fault rupture. So as you can see, the figure to the center, some of the fault in red represent the possibility of the multiple fault rupture that could rupture together and result in even higher hazard or larger ground shaking. Eventually, considering all of the impact, and we can see the outcomes of the hazard level is showing in the center. But if we further take a look, the impact from this kind of the innovation, it shows to the right. We found the significant raise of the hazard in the northwestern Taiwan as well as the southwestern Taiwan, where we have a lot of the urban city over here as well as the two of the metropolitan city in this region. Such kind of information will raise the importance of such kind of innovation, especially if we consider some of the impact to the populated area. Besides the contribution from the geology as well as geomorphology, we also have a new generation of hazard map using the geodetic information. So this is done by our team member Ray and Guan, who proposed two models for the geodetic information. One is the baseline inversion method. Another one is block model that is widely used for different regions around the world. By considering all of this information, and we compare with our geological slip rate, and to eventually use the 24th structure using such kind of a geodetic slip rate, and eventually we got the seismic hazard map, as you can see the figure to the right. We also have such kind of the new definition of the subduction zone parameters or subduction alignment, which is based on the framework of the Shaker Level 3 that proposed approximately 10 years ago. So based on such kind of assumption, we have the interface, subduction interface and the subduction intra-slab, and we have two subduction zone systems. One is to the northwestern Taiwan, and another one is to the southern part that linked with with the Luzon Island. So based on this such kind of consideration, we got the two results. As you can see, there are two Taiwans over here. One is considering the hazard map, the hazard level change for the SA 1.0, which is relatively for long period. Another one is for the low probability event with 2% of incidence in 50 years. Both of them suggest that significant increase of the seismic hazard just because such kind of the mega thrust event could cause the significant amplification of the long period. Not mentioned for northern as well as western Taiwan, we have several metropolitan cities with high-rise building. Such kind of the information could contribute to our subsequent risk assessment that I might elaborate later. We also consider the new logic tree branch for ground motion prediction equation, comparing to the previous generation of our hazard map that we only implemented one single GMPE from locals. This time we consider several branches of the GMPE, but in order to do such kind of a validation, we need to compare our observation. So here is our observation that has a period in between the 1991 to 2020. We have the more approximately about 70,000 of records with magnitude larger than 4.0. In order to validate it statistically, we propose three approaches, as you can see here. So now we have such kind of the data, but as you can expect, we will have a much more smaller event than the larger one. We will have the longer distance than the shorter one. In order to overcome such kind of the data imbalancing, we need to reweight such kind of the distribution and eventually to try to have more or less equal weighting for the different magnitude as well as the different rupture distance. So then we can put it into validation. So what we consider is not only for the local GMPE, but also some of the international ones. So as you can see, the result represented over here. So I don't say too much in detail for this figure, but one thing I would like to mention is if we get the highest score, unfortunately, that means that the performance is bad. So based on such kind of the ranking, eventually we propose two logic tree branches for cross-flow event as well as a subduction zone event. And each of the branch, we consider different GMPE with various weightings, as you can see over here. So by considering such kind of a weighting for the GMPEs, and then we can compare with the hazard level from the previous generation. And generally, we got relatively higher hazard. Such kind of a result is because of the differences in the magnitude as well as the distance scale. Besides of the passive effect, we also have a deeper investigation for the sighted effect. So we obtained the VS30 map, as you can see the figure to the left, based on some of the geophysical investigation, including some of the trenching or some of the geophysical survey, which is done by Professor Chen and Professor Guo. And that means in such kind of a tiny island, we have more than 3,000 sites with the corresponding VS30. We also convert such kind of VS30 data into Z1.0 as well as Z2.5, reflecting some of the relatively longer period of the hazard assessment. So as you can see, eventually we got the change of the hazard in respect of the PGA as well as relatively long period, 1.0 seconds. So we got much more in detail of the seismic hazard, the site amplification for each of the site of our investigation. To summarize all of the impact, as you can see, there are so many Taiwans over here representing the impact from different consideration, including area source, onshore and offshore structure, subduction zone, as well as GMPE. I don't want to say too much in detail, but I would like to draw your attention to the figure, the Taiwan to the right, which suggests that for some of the region, the elevation of the high hazard is attributed to area source as well as some of the offshore seismogenic structure and some newly identified structure in southwestern Taiwan. For other regions, the drop of the hazard level can be associated with the newly definition of the area source as well as the multiple rupture pair due to considering the relatively short return period. We also investigate the impact of the seismic hazard for some of the city scale, especially for the six metropolitan city, including Taipei, which is we say capital of Taiwan. So I don't want to say too much in detail for each of the city, but I would like to draw your attention into several considerations. You will see the solid as well as the dashed line represent the median and the mean hazard curve. So if we take a look, if we compare the both, we will know if we take a look at the median value, it will cause relatively smoother hazard curve, but we will get some of the extremely higher hazard, especially for the very low probability of the incidence, which can be attributed to some of the extreme branches. Second is, if we take a look the hazard level comparison for this kind of city, I would like to draw your attention for the city of the Tainan and the Kaohsiung, which is not far away from each other, but such kind of the hazard curve represent some of the characteristic of the hazard, the source of the hazard. That means for Tainan region, we got relatively higher hazard, especially for the POE above 10% in 50 years. But if we are talking about a relatively longer return period, the Kaohsiung have the significant higher hazard because of some of the neighboring active fault. We also represent the response spectrum for these 6 cities. One thing I would like to draw your attention is, especially for the Taipei city, which is over here, which represent the corresponding longer period has a higher hazard. This is because of we have the new identification of the subduction zone that we have the better understanding through the Sheck level 3. One thing I would like to draw your attention is such kind of the higher level of the hazard, especially for the longer period, will have the significant higher impact for some of the skyscrapers in Taipei, which also a lot of the residents, approximately 3 million people living in Taipei, including I myself and my families. So, in general, what I would like to draw your attention for our updates in our 2025 version is we've already proposed a new definition of the seismogenic structure, no matter that is offshore or onshore. We also integrated earthquake catalog to obtain the new area source. We also have the newly interface and the intra-slab sources based on the Sheck level 3 approaches. And then we also propose the new idea for the weighting of the GMPE. So this is what we have done for the seismic hazard assessment for Taiwan. And as I mentioned, this is the work for our team in the past 5 years. So that means we not only want to just publish that internally in Taiwan, but also want to attract some of the collaboration through internationally. So that's the reason why since last year, we conduct such kind of a spatial issue in engineering geology And we invite several specialists around the world, including Marco and someone from New Zealand, someone from Japan, to enhance the impact or have such kind of the international judgment. We not only want to do the seismic hazard, but also some of the secondary hazard. So that's the reason why some of our paper focusing on the tsunami, liquefaction, as well as the earthquake trigger landslide. Until now, we got totally 7 accepted papers, as well as 10 of the manuscript under revision. One good news is on my way to Croatia, and I got the information that our seismic hazard assessment paper has just been accepted last weekend. So that means I'm very happy to share such kind of the result to everybody. Of course, if you are really interested in how we establish this kind of model in the form of the OpenQuake, please feel free to contact Marco, and he has our source code. Besides hazard, actually we are also involved with some of the risk assessment. So in the past, say 10, 15 years, we try our best to do our first generation of the risk map, but for some of the reason, and we haven't yet done good job as what we have done for hazard. But fortunately, we got we can say first generation of the probabilistic seismic risk map for Taiwan by considering some of the very high resolution of the exposure model. And if you are interested in how we establish our risk map, please feel free to contact Jiasen, who will have the poster tomorrow. So in order to not spoil your fun to interact with Jiasen, so I will just stop here and please go to her poster. Besides Taiwan, we also do some of the assessment for Southeast Asia. For the seismic hazard assessment as you can see, the hazard map to the right is achievement of a collaboration from internationally, including the people from Myanmar, who they are suffering from some of the political issue, as well as specialists from Thailand, Vietnam, as well as Singapore. We working together and try to propose the better understanding of the seismic hazard map, especially focusing on some of the newly innovation along the Sanggan Fault that ruptured last year and caused a lot of the fatalities. What we have done is consider the so-called multiple segment rupture that we know the Sanggan Fault, as long as we define the Sanggan Fault into several segments, considering geological or geomorphological evidence. But eventually we know it could rupture together and cause very, very large earthquake magnitude as well as ground shaking. We also proposed such kind of a time-dependent model. That means we use fault memory and considering the elapsed time of the previous event. One thing I would like to draw your attention is such kind of the work is based on the collaboration between not only based on the local specialists, but also the collaboration between GEM and the Aeon as well as our team. So we are very looking forward to share some of your update maybe in the next government board meeting in December. So I expect this is almost the end of my presentation. That means in the past 5 years, we work with seismologists, engineering seismologists, geodetic persons, as well as some of the geology or geomorphological component, and working together and propose our new generation of probabilistic seismic hazard map. So I'm very happy to share such kind of results with you, not only in presentation, but also in some of the source code in OpenQuake. Thank you.
Thank you very much, Anne, for the present, and thank you also for contributing to the update of the global maps. Are there questions? We have a few minutes for taking questions.
Yeah, thanks for the presentation. I couldn't help but notice when you were showing the map of the block model relative to the faults, that a lot of the boundaries for the block model seem to follow topographic features which could have potentially have been faults and had extended your existing fault database. Are you able to perhaps comment on whether these boundaries were considered in your fault model as well?
I will try my best to answer this question as long as I am not a geodetic guy. So what they are doing is try to figure out how to define the block first. And of course, there's some of the arguments. So is if you want, and I can ask them for some of the manuscript. But one thing I would like to mention here is we not only consider geodetic model independently, but we also compare our geological model. So that means if their seismicity rate is comparable, and then we will get the weighting. If there are so much difference, sometimes we will be hesitant because such kind of a geodetic slip rate, no matter that is block model or another baseline inversion method, could be significantly affected by some of the concern. For example, there's a mud diapier in southwestern Taiwan, which could cause creeping of, I don't say not only the structure fault as well as the block. So that's the reason why we pay a lot of attention, especially in southwestern Taiwan. As you can see, they are so complex over here because of such kind of concern.
Maybe I have one. I noticed that the NGA West are not performing well, and I was wondering if you've been trying to understand or figure out the reason why a good chunk of the NGA West are not working well in Taiwan.
Sometimes, first of all, I would say this is data driven. So that means we just put all of the available GMP and then to put it for validation. Sometimes you can say that is unfair because for those GMP obtained for Taiwan catalog, and then we use more or less a similar database to validate it. So that means this is a little bit lose the spirit of the AI or such kind of the big data validation. But this is kind of the comparison. And the second is, if you are really interested in that, I expect Jiaqian has submitted the one manuscript, which is under review, and hopefully they will publish that soon. Yeah.
Thank you. If there are no further questions, we can move to the next presentation.
Thank you so much.
Okay, good afternoon, everyone. Thank you for being here today. Before starting, I'd like to thank the organizing committee for invitation to this special session and giving the opportunity to give our initiatives towards a new seismic hazard model for Italy. Okay, so this slide presents the outlines and the structure of my talk. If you realized in the title, also, I'm not going to talk about only the scientific issues in this presentation because it's an ongoing project. And first, I don't have complete results yet. And the second point, I think, is more important, that at the beginning of this project, we spent lots of time and energy to organize our work. So I think this it could be really interesting for our discussion, seeing that there was a discussion at the end of this special session. I wanted to share with you some experiences that we have faced with at the beginning of this project. So my talk, I will start with the motivations and the objectives. I'm trying to understand. Okay. And then structure and the governance, so the organizational framework. I will mention primary and the secondary project outputs. I'll give more detail on that. What does it mean? And finally, methodology, briefly, methodology we used and the models developed, and the progress status of the project, and the activities up to now, and the milestones, next steps, and finally conclusions. Okay, motivations and objectives. I have much more than to say in one figure, but the project started just before, shortly before 2025, to develop a new PSHA model for Italy by the end of 2026. So it's a 2-year project coordinated by the Seismic Hazard Center at INGV. So the project is designed by this date, seeing the Eurocodes, knowing the Eurocodes are going to update it to 2028 as requested, and in agreement with the Civil Protection Agency and the Superior Council for Public Works, that this seismic design regulation is the official authority to this kind of change. These are the requests done in agreement. So it's a really limited time, of course. Our aim is not only to update previous national model, as I'm talking about the MEPS 04, is still present the reference model for the current Italian codes, but also the MEPS 19. This our project we call ISHM, builds on the scientific experience gained through this model. While not formally adapted for regulatory purposes, it remains the most recent national seismic hazard model developed for Italy. So we are taking advantage all these database prepared, the methodologies applied, so it's somehow we are updating and adjusting everything here. So, of course, the ISHM aims to provide a scientific foundation for future seismic design regulations, not only, but also the land use planning, risk mitigation strategies, by integrating updated multidisciplinary dataset, well-established modeling approaches, and international best practices within a transparent way. Okay, this slide presents the structure and the governance of the ISHM. It summarizes a complex process involving several components and the stakeholders with clearly defined roles. These are really important. The project is coordinated by Seismic Hazard Center in close collaboration with the Civil Protection Agency, and the project core team leads the scientific activities and coordinates the decision-making process. And then we have the dedicated working groups. They are developing the seismicity and the ground motion models. And they also perform the hazard calculation and model evaluation and testing. So we have advisory panel, provides independent scientific review through the project. We have also strategic stakeholder group support the project by ensuring its applicability and the operational relevance. So this is an important point. We have important groups for us because it's a new, just to make sure that the model is not scientifically sound, but is applicable. So is applicable means that in all countries, you have to see the percentage change in the hazard, how the social economical impact in the country. So these are all important points that we have to really discuss and discuss and somehow take the decisions. Okay, this slide summarizes the ISHM project and team. We are working groups and the coordinators together with the expert modelers involved in the various thematic areas. And the workflow highlights the interaction, continuous interaction and collaboration among the teams throughout the project. Overall, about 30 researchers are working full-time on these activities. Okay, here I'm presenting the members of the advisory panel composed mainly of the international experts with specific expertise across the different thematic areas. So in particular, these experts have intensive experience in managing complex seismic hazard projects. So applying innovative methodologies, helping to ensure that the project remains aligned with the international best practices. We have to guarantee also this one. So the strategic, however, the strategic stakeholder group on the other hand brings together national experts. So with direct expertise in the seismic hazard and the risk issues in the Italian context. So with the goal of the promoting the practical applicability of the model at national level. So in this slide we are presenting the roles. We think that is really important, the level of involvement also, and make sure that everybody is involved to the process, and the responsibilities and the official authorities. So as mentioned already, Seismic Hazard Center is the responsible for developing the model, while the advisory panel provides independent reviews, strategic stakeholder groups contributes, defining requirements and priorities by assessing the applicability. We have the INGV Board of Directors provides an institutional approval, because these endorsements, approvals are really important steps after all the experience that we have in Italy. And also there are no guidelines and roadmaps as well defined. So we have to make sure that everything is in the right way. So we spend really lots of time on this, figure out how to organize, involve lots of people. And while we have also not only the civil protection, but the civil protection has this major risk commission in consulting this kind of activities. So also the Superior Council of Public Works involved in this process. Community involvement, transparency, applicability, all these keywords are really important at the beginning of this kind of projects. And community and stakeholders' involvement is provided through workshops and the national, international activities. So the transparency and the reproducibility and traceability is performed in the hazard model is being developed in the OpenQuake framework, so in collaboration with the GEM foundations. So the model applicability, I don't want to repeat again, but we are planning to use having a different outputs. This is stakeholder needs. We have to listen stakeholders what they need and prepare these outputs can be available for each of those. Okay. This is, I don't expect you to look at in a detail, but just a slide that highlights the main interactions between the project team and the advisory panel, strategic stakeholder group. These meetings provide a scientific guidance, and the stakeholder feedbacks are important for us. So this in somehow support the alignment of the project outcomes with the operational and the regularity needs. So in the next week we are going to have another one. These are really time consuming because you have to prepare your model, write a report, get the feedbacks and adjust your model, refine your model, but this is what is needed, in fact. So I know that a 2 years project is not really easy to manage, but we have a great advisory panel and stakeholder group that they are really helping us a lot. Okay, so this is the priority and secondary outputs that I was mentioning. This comes from the strategic stakeholder groups. So we are trying to understand and define the required products and share updates on the project also with this inform the stakeholder groups. So these are at the moment what we have. There are lots of requests looking at the return periods and also including different components, not only the horizontal but also the vertical definition of the components and the site classes. The priority outputs we negotiate with the stakeholder groups, asking that what do you need just for the design code application? So I'm going to give you this one only, because project is impossible to conclude in 2 years. So we are putting something as the secondary outputs that it could go beyond the end of the 2027 in somehow. So because we need to prepare the hazard toolbox, accessibility, web services. Of course, if we are good to get a good model and convince them this time everything is okay. So this is the project timeline. We are now more than half through the project with roughly 6 months remaining before. So the project is now, I can say, operational and focused on achieving its scientific goals and deliverables. It was difficult at the beginning. So just let me briefly introduce the main database in the project that we are considering. So this is the key input, the seismicity catalogs, of course, in particular, the historical and the instrumental catalog. So in Italy, it's good or bad, I don't know. We have the earthquakes, we have the fault database, geodetic information. So just we have to handle in the right way all this information. Nothing is missing up to now. So we are also paying special attention to volcanic areas, especially Campo Flegrei. Probably you are heard about that, where the seismic activity has increased significantly in the recent years. So the Civil Protection Agency is requesting a special attention to these areas. We are now monitoring networks. They are providing more detailed pictures of the seismicity, particularly in the Neapolitan volcanic areas. Okay, so these are another important input data sets for the seismicity models, including fault database, focal mechanism, and hypocentral depths and the geodetic information, all available at the national scale. So what we did at the beginning of the project, we frozen the data set at preliminary version to let the modelers to use database, but at the same time, we updated all of those. And we had the new version of these databases a few months ago. So what we did, thanks to these historical catalogs is available for Italy, we evaluated the catalog completeness. We spent more time on that because containing really large earthquakes in different areas in Italy. So catalog completeness using both historical and statistical approach across 6 macro areas in Italy. We also assessed the impact of the different declustering methods that you know, Gardner and Nopov, Grunthal, Zeliapin. We were all trying if they are really providing the Poisson process after this analysis. So we realized that the results show that all the clustered catalogs are consistent with the Poisson process, so supporting their use in the PSHA. So within the project, we are developing 4 families of the seismicity rate models: area source, smooth seismicity, fault-based, and geodetic models. So in addition, we have the dedicated models for the main volcanic and the subduction zones. We have 2 main subduction zones in Italy and several volcanic areas. So all these models, of course, will be integrated within a logic tree framework in somehow. We are also accounting different epistemic uncertainty in the seismic data. Not only the completeness, but we have the regional completeness magnitude, the slip rates, maximum magnitudes, and b-values. B-values also spatially variable in Italy. Okay, this was the 4 model because we want this. The model uses different approaches and different databases, and somehow their definition is different. So we are currently updating the models following the advisory panel feedback. At the same time, we are applying these different tests, N-test and S-test. These are going to help us to give a certain weightings into the logic tree. This was the table we have prepared as the preliminary SRM components presented in February. We had an advisory meeting in Rome, but then following, as I said, their feedback, these models now is ongoing and with a particular attention given to treatment of the uncertainties. For the subduction zones and the Neapolitan volcanic areas, we are trying to use 3D dimensional adaptive kernel to capture the complex spatial and depth distribution and the seismicity in the volcanic and the subduction environment. So in the Etna area, we have a hybrid approach that takes into account three components as the shallow volcanic tectonic seismicity and background seismicity and deep crustal seismicity associated with several historical earthquakes. A few information and models regarding the ground motion models. This slide is presenting the final decision we took after, again, advisory panel. So we are going to use the backbone approach, and then the new regionalized ground motion model is coming out using this different data set, ITECA, and is this global near source databases with the regional correction factors is already published by Brunelli. We have the source and the path effects, and this is also help us to take into account epistemic uncertainty. With this backbone approach is consistent with the methodology adapted in the European seismic hazard model. So we have already these standard deviations as a function of periods, the magnitudes, and we have the, here I'm just bringing the backbone logic tree. It's going to be used in the project. So if you look at the volcanic areas, of course, the existing ground motion models are not fully suitable for the backbone approach. We are developing an integrated database, volcano-tectonic earthquakes from the main Italian volcanic areas. So this database is being used to develop the backbone, GMMs, and the logic tree framework that explicitly accounts for the uncertainty in ground motion prediction for volcanic earthquakes. So the differences between volcano and volcano that we will going to use taking account to observe the data is the same for the subduction zones, and the same data set is going to be used to distinguish the subduction zones from one to another. So these are all is on the way, but we are almost ready to use. Of course, this is model testing and comparative evaluation is requested by a spatial stakeholder group. So what we are planning to do, this is going to be also one of the milestones requested by the strategic stakeholder group, the comparison with the MPS 0419 and the European seismic hazard model. So they want to know the differences that we are getting and somehow discuss this and compare also with the macroseismic data that we have really available in Italy from the historical earthquakes. So this is again the timeline. So here we are planning everything at the end of the year, but probably the priority outputs and at the end of this 26, the beginning of 27, we will have other secondary outputs. So I have not much to say at the moment in the scientific part of the project, but we can say clearly that the future perspective and the preparation, we want to ensure that any practical application of national hazard assessment remain grounded in a robust and well-validated scientific framework. We have to guarantee the model producibility and the accessibility through toolbox and the web services. I think the more important job is needed in Italy, at least, to prompt the development of the roadmaps, regular guidance to support future updates of the Italian PSHA model and its evaluation, implementation in building codes. Thank you for your attention.
We have time for a couple of questions.
Thank you for that. I was curious if you have any plan to do model validation with earthquake occurrence in addition to the ground motion data, but looking, for the source characterization, comparing, if there's going to be any comparisons of that against, existing data.
Okay, you are talking about the seismicity rates. Yeah, I think I mentioned. Yeah. Of course, we are going to. Yeah. Maybe I passed so quickly.
Or maybe I was late.
Probably.
Another question? Okay, if not, I have one.
Yeah, sure.
In your Gantt chart, you have one explicit row in which is adding or modeling epistemic uncertainty. Is that because the approach that you are planning to use for incorporating epistemic uncertainty is, let's say, sort of ensemble model, so with plenty of different models implemented independently or almost independently?
So you are talking about this one?
The purple one, construction of the logic tree.
Yeah, construction of the logic tree is going to be ensemble model.
Okay.
Yeah. Okay. Yeah, sure. But how is going to be? It's I was really scared that you are going to ask this question. Hopefully not.
No. I don't want you to spoil what you're thinking.
No, we cannot do that.
Members of the external
We have been
advisory
thinking
panel.
twice just putting these 4 seismicity rate models. Should it be there or not?
No. Okay, thanks a lot, Ivy.
Thank you.
We are moving to the last presentation.